SwayamPrabha. Digital India. Educated India.
Welcome to the course of Intelligent Product Design. Now we are in the phase of sensors, and today I am going to talk about some of the traditional sensors that we will need for designing an intelligent product. So, the part 1 of these traditional sensors will be mostly non-optical sensors, except 1 or 2 where I will show you that an optical equivalent is also available. So, let us start with the sensors. So, now my organization of talk will be based on the fundamentals of sensors transducers, followed by position sensing, sensing of direction and distance sensing. First of all, it may occur to you that why do we need separate sensors in a system? Now, there are many reasons of it. The first point is that we need to always know the nature of the measured signal. So, whether the signal is in a steady state or in highly transient state, or whether it is a periodic signal or narrow band or broadband. So, that actually would need separate sensors in order to sense these type of characteristics of the signal. Then the required frequency content of the process signal many times will be also of interest to us, that what are the frequency content, because usually a signal will be in, let us say, time domain. So, this is time, and let us say something like a voltage, and you will get some signals out of it. Now, instead of having these time domain signal, many times we will be interested to know that in the frequency domain, let us call the signal in frequency transformed way as V bar, then what is the frequency domain signal that is coming out of it. Okay? So, because that will tell us that what are the major frequencies that are containing in the system, etc. Now, the signal to noise ratio of the measurement is of another concern, because unless the signal to noise ratio is high, in the sense the signal content is higher than the noise, it becomes difficult to get anything meaningful out of the sensory data. Then of course, there are concerns of available processing capabilities, controller requirements, required accuracies. All these things determine that the number of sensors, how many we will need in order to completely comprehend the scenario. Okay? So, what we call a virtual environment, to generate that virtual environment, to generate a digital twin, these are the factors that will tell us that how many sensors are going to be required. Now, we will start that with a 2 sensor application first, which is very simple, and that will be in terms of position sensing. Now, let us think of position sensing first from a bio-inspired point of view. Let us think of a case history of lessons from the navigating birds. 2 specific birds, golden plovers and Arctic terns, are known to navigate thousands of miles from Arctic to almost Antarctica, 20,000 miles round trip travel in the case of Arctic tern, unbelievable. Now, they fly by day or by night, most of the times over the featureless seas, oftentimes completely out of sight of land, and many times above the cloud layers, yet they manage to navigate, they manage to come to the same point 10,000 kilometer away every time. How do they do it? They do not have any GPS positioning tracker with them. So, how do they navigate? Well, there are easier ways for land based navigation, like the landmarks that the homing pigeons do. They can remember the landmarks very well, but of course, within a radius of 20 kilometer they can do it. Some of the birds can actually use sun as the compass. Depending on at what latitude they are, they know that, like in the fall, the sun is located directly south at noon and moves approximately at the rate of 50 degrees per hour. So, that at 2 p.m. means south will be 30 degrees to its left. So, they get an intuitive sense, and then they can use sun as the compass, because sun has a source of warmth, heat. So, depending on which way the heat is hitting them as they are traveling, they can understand whether they are going down south or southeast or northwest or not. A few birds also have the capability to look into the constellations at night, because for some birds they mostly travel in the night time, and daytime they feed themselves wherever they stop. But there are even more difficult ways of navigation. For example, if there is an overcast day, then there is no sun. How would the birds then still navigate? Well, one of the ways some birds do is by detecting the pattern of polarization of light in the sky, that they can take it as a cue in terms of the direction. Then stellar navigation also involves understanding different constellations and their motion pattern. So, with respect to the Earth's rotation, it is observed in planetarium that many migratory birds, they actually continuously flew in the opposite direction of the axis of rotation of the stars, regardless of the true position. So, which means they understand to some extent that how the constellations move, and then accordingly they set the directions. However, the story goes far beyond than this. It is now found that many of these birds, their eyes itself are actually magnetic sensors. So, they take magnetic cues from their eyes, and surprisingly, not only the birds, some of the vertebrates like sharks, rays, alligators, sea turtles, they also use a very similar technology. In fact, it is noted that the caged birds orient southward even when they can't see the sky, and in the early experiments surrounding the cage with steel has been done to eliminate the magnetic field cues that can come from the earth, because as you know that the earth has, other than the geographic poles of north and south, also has the magnetic north and magnetic south. So, with respect to this magnetic north and magnetic south, these little dipoles on a bird's eye, so if you consider these to be a bird's eye, and there are a lot of these dipoles around the eyes of the bird, just to give you an idea. Okay, so north, south, and like that. And it is also, so this is the bird's eye, let us say, and also depending on that around what position we are traveling, the earth is continuously rotating, and then it has its own north south. Okay. So, with respect to this magnetic north of the earth, because earth will be having its own magnetic flings, okay, that is continuously happening. So, these magnetic fields are going to interface with the magnetic fields that is there in the bird's eye, and that will create a sensation in their eye in terms of giving a sense of direction. So, it works almost like a compass, each element in the eye. So, they can feel in the eye that which way they are going. So, like these, the biological systems can sense the direction. Well, let us think of now the principles of position sensing. What does the position sensing requires? Well, it requires two informations. One is the distance from a fixed position, and another is the direction. In fact, if you are in space, you may need actually 3 information, not just 2, because you need to also know what is the altitude or height. So, now because these 3 informations, 2 to 3 informations are required, some are distance and some are direction. Let us first focus on the direction, that how do we sense the direction? What are the traditional sensing systems for sensing the direction? Well, of course, one of the most ancient one is actually the magnetic compass, and also similar to that there is the sextant plus chronometer together that the captains in the ships they used to use. While sextant is used with respect to sun, for example, but magnetic compass can be used day and night because it is with respect to the earth's magnetic field. And then you have a better one, that is called the Hall probes, based on a very similar principle. We will talk about it soon. However, can we have something which is even independent of this magnetic field? Well, gyroscope can exactly do that. There are 2 versions of it, mechanical and optical, we will see to that. Now, these are the sense of direction. These are, we can say, the global direction sensing, global direction, okay, which is needed for navigation. But sometimes you do not need a global direction, but you just need a local change that can happen. So, these local changes, localized sensing, there are again 3 to 4 sensors specifically for localized sensing, like tilt sensor, like potentiometer, piezoresistive sensor and magnetoresistive sensors. So, we will look into all these things, particularly some of the most important things. For example, in the global direction, we will start with the Hall probes. Well, that would also be necessary in order to understand then what is the Hall effect. Hall effect is based on very interesting phenomenon. We always know that an electric field passing through a wire creates a magnetic field as well. Now, what about if we do not have a wire, but if we have a plate like this, okay, and the current is flowing on the plate. Now, in such a case, what you would see is that because of this finite width, as the current will travel, and the current travel means electrons are traveling in one direction, but in the plate they will concentrate in one side. So, there is a sidewise potential VH that will be developed in the system, and this sidewise potential may get changed if the magnetic force that is working on them, if that gets changed. So, Hall effect is exactly based on this. That means, we know that there is a earth magnetic field continuously working. Now, already the electrons on a wider system like this, already the electrons are shifted in one direction and you have the VH. And now, this VH, when it interacts with the earth's magnetic field, it takes a certain value, because that force comes in addition to the force that actually shifts the electron in one direction. And then the resultant of these two continuously changes as you change the position. So, that is what is the Hall effect itself, and the Hall voltage is simply a function of the current, a function of the width B, and also inversely proportional to the thickness of the system. And then there is a coefficient which is called RH, which is a Hall coefficient. The instrument looks very small like this, a typical Hall sensor, and typically it works like a switch, like a bionic sensing system. Now, this of course needs the presence of magnetic field, but what if we are thinking of a place where the magnetic field is very much distorted, the earth's magnetic field, maybe because of the presence of the high voltage transmission lines, railway line carrying current or things like that. Well, in such a case, one instrument can always be of very good use. This is a completely mechanical system called nothing but a gyroscope. What is the basic principle of a gyroscope? Well, as you can see in this figure, that a gyroscope can have rotations about 3 axes. So, this is one axis by which it can have rotation. Then this is another axis, this spinning axis that has been shown here. And then of course, you would be having another axis here, that is, you can see it or you have to visualize it, which will be perpendicular to this system. So, now you will be having 3 axes. So, the gyroscope, the rotational gyro is actually moving about one of the axes, right, like this way it is moving. And then let us say that because of my change of position, this gyroscope has a different amount of moment or torque coming into it. In that case, the gyroscope will always try to conserve the moment of inertia, and this tendency to conserve the moment of inertia can be actually sensed. So, if you have a kind of a torque sensor that can sense that what is this resistance to the change that is happening, which will give you the angle or the direction with respect to the initial position. So, that is what the gyroscope or the gyro would do. Now, there can be many different types of gyros, like one I have shown is a fully mechanical gyros. Then there are optical gyros, something like fiber optic gyroscope, ring laser gyros, then the MEMS-based gyros and the gravity probe system, which is used in the very sensitive measurement of direction. So, there is one important thing that governs the criteria for the choice of the gyroscope. So, which appeared in this particular paper. Okay. So, I have just taken this particular figure to illustrate it, that if the bias stability, that is how much of degrees per hour its shifting would happen, if it is low, then one should go for mechanical system. If it is slightly higher bias stability, like in missiles and all these, then one should go for a ring laser gyroscope. Now, beyond that, there are good examples of MEMS-based gyroscopes, and for rate and integrating gyros, these are always used for the flight control type of systems. Also, there are some very special systems like interferometric fiber optic gyroscopes, IFOG. Then there are these quartz or dynamically tuned gyroscopes, which we call DTG. So, you can see that depending on the bias stability, you can choose a suitable kind of a gyroscope for your utility. Some of the gyroscopes are having really very broad band bias stability, and some are narrowly placed. Another thing also you have to keep in your mind, that in the y axis what we have is scale factor stability, and that means the high performance. So, high performance also would mean that it will be of high cost, whereas if it is lower here, then it is low performance and low cost and high volume. So, depending on at which region you want to keep your sensor, you can actually choose what type of gyros you need to utilize in your system. Now, as I told you, there is ring laser gyroscopes. This type of gyroscopes are also known as optical gyroscopes. They work on a system called the Shannock effect, and this was the cause of the Nobel Prize of Shannock. So, what you get here is that you have a system in place which has several mirrors in it. Okay. Now, you have a beam splitter, so that the source beam is splitted into two parts. One is going right, another is going straight, and then each one of them is taking the full turn, and then it is coming to the detector. Now, if the entire thing is rotating, one side, so suppose there is a rotation here. So, one side the laser is going with the direction of the rotation, and in another side it is going to oppose. So, there will be a little, very little phase difference between the two, and that phase difference can be utilized in terms of predicting the direction of the system. Now, we have talked about the global direction sensing. Let us look into some local sensing. One of them is a very famous tilt sensor. Tilt sensors, what they do is that you can think of that there are some electrolytes here and there are some electrodes here, A, B, C's of them. Now, if there is a tilt in the system, if there is no tilt, then of course they are all flat. Okay, no tilt, they are all flat, and that means that VA, VB and VC, they will be all same under no tilt condition. But if there is a tilt, then there will be lesser area here and more area here, which means that VA will then be greater than VC. So, thus the difference of voltage will be a measure of how much of turn the system has taken place. So, the tilt you will be able to know. Now, let us look into the distance sensing. What are the different types of distance sensors we can utilize? One of course is radar, which is based on electromagnetic wave, and then there is sonar. So, the principle in both the cases, even including radio beacon, is very same. You send a wave and the wave gets reflected from the object. So, as it came back to you, so you need to have always a transmitter and a receiver. As it comes back to you, you measure either the delay between the two or you measure the interference pattern, because the two signal, the one which is received and the initial signal will have a bit of a phase difference between them. So, through that you can try to measure the distance. Of course, in a very small scale, you have other type of sensors like linear voltage differential transformer LVDT, which is between 0.1 millimeter to 1 meter, and then capacitance based sensors, potentiometers and some form of optical encoders. So, let us look into these radio beacon plus ultrasonic, which is used very much in the robotics application. So, what they do is that there is a robot which is sending the signal. So, we can call it as a transmitting robot. Now, it is sending two signals at the same time, radio pulse and the acoustic pulse. And let us say it is going to the receiver robot, and from there when it is coming back, because the light waves travel in a small area at a very fast rate, this is like 15 to 20 kilometer. So, there will be almost no travel delay. On the other hand, the acoustic pulse is heavily medium dependent. So, there will be some delay. So, this delay that is happening, this delay is a measure of how much or how far away the robot is from the team leader. Okay. So, the team leader is sending the two data from which the leader can make out that how far away this fellow has gone, and this is used for popular games like in Japan the robo soccer is used, there this kind of a concept is used. Now, another possibility of local measurement is dead reckoning inputs. Dead reckoning inputs is particularly important when we drive our car and let us say at a certain location there is no Google map available. We call such locations to be GPS denied atmosphere. In such cases, from the point this is happening, there is a heading sensor that senses the input from the odometer. Odometer rotates simply measures the number of rotation of the wheel. So, input from the odometer, and also it takes the input from the backup signal of that particular place. So, these two things together gives the automobile an idea of how far away it has gone from a known position. In the local sensing, particularly for vibration, we use another type of a sensor which is known as a LVDT construction. Now, LVDT sensors, it is going to have three different type of systems in it. Okay. One is a primary coil system which works against the movable core here. Another is there are two secondary coil systems. Okay. They are in the side of the primary coil system. So, now how would this system work? Well, depending on what is the position of this movable core, the movable core is going to create a magnetic flux between these the driving core and these pickup coils. So, that is something that one has to measure, and the difference between the two will actually tell that which way the system is going, and then it can be a measure of the displacement of the system. That is the idea that is broadly mentioned here, that machine you give a displacement and you have DC power supply and an oscillator, and you have the secondary pickup coils. So, if there is a displacement that is figured out by this signal, but the signal can be modulated. So, you need a demodulator, a low pass filter, and then you will get a DC amplifier and the final analog voltage related to the system. So, it is a bit complicated, but it is very precious. Now, another system that is used for short distance movement is called the capacitance based sensor. In this case, there are two things that you can measure. One is that the distance between the capacitance, which is d, and another is the overlapping distance between two capacitors. So, both of them together, if we can measure, then we should be able to predict about that how, in which direction a system is going to move, the motion would be generated. So, the capacitance based position measurement is like this is the expression of a standard parallel plate capacitor, where A is the overlap area, x is the distance, and f0 AR is they are actually the absolute and the relative permittivity of the system. Now, there are various ways by which you can develop a capacitance sensor, like you can do it in a rotating plane. So, that becomes a rotational displacement sensor. You can do it in a moving plate diaphragm. You can do it in a capacitance bridge. So, there are many different ways by which you can use the capacitance based sensor. Let us now come to another heavily utilized system for angle detection, and this is nothing but the potentiometer. Potentiometer is so ubiquitous that you can say almost all of us possess potentiometer. Like every single fan in our house, the regulator of it has a potentiometer in it. So, what does the potentiometer do? It is very simple. It is just like the concept of the variable resistance system, like a sweeper variable resistance, that if the system moves, then this these indicator moves, and depending on how far they are moving, one can predict that how they are going and which way they are going. Are they going the correct way or the opposite way? So, all these things you can check in this system. So, the potentiometer, the use other than this particular thing that which way they are moving, one other important thing is that what is the kind of the wiper arms position, whether there is linearity in the system, okay, and whether you will need a voltage stabilizer or not. So, all these things together can actually help you to design a potentiometer. So, what are the limitations and advantage of the potentiometer based system? Well, first of all, the force needed to move the slider against friction and arm inertia, that is provided by the displacement course, but that needs a good bit of actually designing the system. Then the high frequency or high transient measurements are not feasible in such a system. Friction and inertia resistance in the local scale is, however, all right. Variations in the supply voltage may cause error in the system, and electrical loading error can also happen, and the resolution is limited. So, the limitations and advantages of pot further are in terms of mostly the wear out and the heating up of the system. They are not very expensive, so that is good side, and potentiometers provide high voltage output signals and require no amplification additionally. So, you do not need a third source in order to amplify the signal. The transducer impedance can be varied simply by changing the coil resistance and the supply voltage. So, this is typical of a optical potentiometer system. However, this needs a kind of a optical force to be present in the system. So, that is one of the kind of a problem with this system, implementation problem. So, I have mostly tried to cover some of the basic sensors in this talk, and in the next talk we will talk about the smart sensors. Thank you.